What we're going to talk about today is we're going to start going down inside the machine and understanding how hardware could be used to actually execute those instructions that we've just been talking about the last 2 days. So we're sort of doing this descent down, and eventually, we're going to get to, let's see, is it atoms or molecules? Well, we're going to get down to physics down at the bottom, okay? Elementary particles down at the bottom. And that's what we're going to do for the first 2 weeks of the course. And then in the last third of the course, we're sort of going to go back up to the top and talk about all sorts of modern issues of performance and so forth. But anyway, for now, we're just keeping on peeling the onion more and more. So here's the kind of components that we're going to build the computer out of. We're going to have all sorts of devices, and don't worry about it right now. Of course, as usual, I'll go into these over and over again. But we're going to have a device called a register, which is going to be sort of the primitive element of memory, and it will be able to remember a piece of data that we put into it here and take a little snapshot. It's going to work kind of like a camera. Then we're going to have another device which is going to be called a multiplexer, and that's going to be used to select amongst two pieces of data, the one marked 0 and the one marked 1, depending upon some control input over here. And then we're going to have something called the register file, and guess what this is going to be used for? For holding registers 0 through 31. Except in the case of register 31, it'll have a pretty easy time because it just throws out the bits and produces a 0. But that register is going to have two paths for doing reads, because we'll want to read two registers at the same time to combine them in some kind of operation, and one path for doing a write, which is going to be used to write the result back to one of the other registers. We'll also have this arithmetic logic unit we've been talking about that's going to take an input A and an input B, and depending upon the computation we tell it to do, we'll do a calculation on the inside and produce a result over here. Finally, amongst the blocks that we're going to use is going to be an instruction memory over here, and that will have an address input saying which address in the memory we want to have access to, and that again is how far from the beginning do we want to read a particular word. And it'll also have a data port which is going to be telling us what the data is at that particular address. We'll also have a data memory over here which we're going to be using for reading and writing different data items in the memory when we do loads and stores. Now, these are going to be shown as different blocks, but in fact they are nothing more than different ports, different access points into the single large, slow main memory we talked about the last time. Okay? So anyway, that's the overview, and again, don't panic if you don't remember it right off the top of your head. Let's back up even more for just a second and remember exactly what we're trying to do. We have a processor that sort of looks like this. Here's the big main memory over here on the right, and we have a program counter that points into a set of instructions that are 32 bits wide that are inside of that memory. We also have a register file starting at register 0 and going all the way through register 31, and you remember the last one is always 0. And of course you remember the particular mode of execution, which is that we find out where the program counter is, we find the instruction that's in there, first increment the program counter so it is pointing to the next instruction to do, then we execute that fetched instruction while this program counter is pointing to the next one, and then we go and do it all over again. So while the instruction is executing, we can expect the contents of the PC to not be pointing to the instruction that's executing now, but to the one after, to the next one. And that'll be important in understanding where these plus ones come from some of the time in the system. Again, here's the format of the instruction. We had 6 bits over on the left-hand side that told us the opcode, and then we had 3 operands. If they were all registers, there was RA over here, 5 bits. This stuff wasn't used. RB over here, 5 bits, and RC, that being the destination. And in the case where we wanted to substitute a 16-bit constant instead of the contents of RB, we had just this register RA followed by the 16-bit constant followed by RC. And again, reviewing once more, we have a typical operate class instruction like add or subtract. And what did that do? Well, we specified RA, RB, and RC. And the contents of register RC was loaded with the sum of the contents of RA and the contents of RB. Or in the case of the constant, we took a constant 16-bit number, did something called sign extension, and for now all you need to know is that that takes 16 bits and extends it to 32 bits of the same value, whether or not it's positive or negative. And it adds that constant to RA, puts the result into RC. Here's how we do it. And I'm going to spend a lot of the time on this diagram, and you're going to see probably 6 or 7 different copies of this diagram with different parts in red throughout this whole class. And actually, one of the things we need to figure out here when we print these notes is how to print it out so that the red is clear, because if you print it out in black and white, it probably won't look too good. And for those of us that see in black and white, I think year one, even if we printed it out in color, it would still look like it was black and white. So perhaps what I'll do right when the class is done, I'll figure out some way to bold these lines, and we'll just get thick black lines. But anyway,
You could do it in blue.
oh yeah, what is a good color? Blue? Okay, but
Certainly lighter colors.
okay, but this red looks just like this black.
Which red?
Okay. Well, so what I'm going to do for the lecture now is I'll point it out, okay, and then it'll be clear, and then in the notes we'll fix it up. Okay. Here's the architecture of the machine, okay? And when you look at this thing, again, it's like opening up the hood of a car, and you say, oh my God, there's a gazillion wires in there. But the truth is, it's only, like I said last time, gas, air, and spark, right? That's all you need to make a car work. And it turns out that all you really need to make a machine like this work is memory in the form of registers and the memory files that we have here, function operations like the ALU that's over here, and these things called selectors, which are these trapezoidal things here, the sort of triangle-shaped things. And we're going to talk about how those individual parts work, but for now, let me explain that this diagram right here shows exactly how we would do an operation like register C gets the contents of register A plus the contents of register B. And very, very briefly, because I like to say things over and over again, here's how it works. The program counter is stored over here. Okay, that's the program counter register. The output from the program counter comes down here and goes into a module which says +1. So this will increment the output of the program counter, and then that goes down here. And then it goes to this device which is called a selector, which, depending on the input over here, which is called the program counter selector, PCSEL, it chooses either this left-hand path, like I've drawn right now, or it chooses the right-hand path. If PCSEL is a 0, this thing chooses from the left. If PCSEL is a 1, this thing chooses from the right. And then the result comes down here, and it turns out that this register down here, which also says PC, is actually the same register as this one up here. This diagram here, if you see what the title is, says it's a descending data flow view of the beta. In other words, the data only trickles down as if by the force of gravity. And what that means is that this stuff down at the bottom, some of these things correspond to some of these ones at the top, because of course in order for a computer to work, the data has to have feedback. It has to go around and around and around. But in order to understand it better, we're going to view it only going top down, except that the data that goes into this guy is going to reappear in this one for the next instruction. So PC gets incremented by 1, gets chosen by this selector here by choosing the left-hand side, and then gets written back into the PC right here. And that's how we increment the PC. Most textbooks will show you this drawn with these two boxes as one box and a loop showing you PC gets PC plus 1 and a loop going back to the top. But that's somewhat confusing, and this is a little bit easier, I think, to say, okay, this is the read side of the PC register, and this is the write side of the PC register. Okay, here's where it gets written, here's where it gets read. Very briefly, and again, I'm going to go over this again, so don't worry. The PC also goes out over to here and goes into the memory. And notice the memory here actually has several ports. Here's one. Read address 1 is an input here, and read data 1 is an output here. And so this is one portal to the big, slow memory. And whatever address you put in here, the memory looks up the contents of the address that you give it and spits out the data corresponding to what's at that place. So this is looking up the contents of the PC is being used to fetch what? An instruction. Okay, and that pops out of here, gets selected by this thing called ISEL, I for instruction, the instruction selector, goes over here, and the instruction pops out here and then is looked at by all of these parts right here. Now, what are these parts? Well, it takes those 32 bits that come out of this particular selector, and it takes the high order 6 bits, bits 26 through 31, and it calls those the opcode. Because if you remember, the left-hand 6 bits of this thing were the opcode. That says, okay, those are the opcode. It takes bits 21 through 25, which are the next 5 bits, and says those are register A. So it's just breaking apart this 32-bit word into several fields. It takes bits 5 through 20 and calls that C, the constant. And that's going to be true for those instructions which we have a constant as the second argument. It also takes bits 5 through 9 and calls them register B. Now notice there's an overlap between the register B and C here, and only one of these will be used depending on whether the instruction is the type that has a constant in the middle field or a register number. And then finally, the last 5 bits, bits 0 through 4, are broken off of this 32-bit word, and those are register C. Now, it turns out that for the operate class of instructions like add, what you want to do, and if they operate on 2 registers like this, contents of register A operate with contents of register B, put the result into register C, you select over here the register B field for this path, and register A comes down here, and they go into 2 different read ports again, but this time not on the big slow memory, but instead on the register file. RA1 results in RD1. The address goes in here, a number between 0 and 31, and RD1, being a 32-bit data item, pops out of here, which is going to be the contents of the register specified by the 5 bits that go in here. In a similar way, here's another port on that same register file, and 5 bits are going to go in here and going to say what RB is, and that register data will come out of the bottom here. And so what will pop out of here is the contents of register A and the contents of register B. Another set of selectors, the A selector and the B selector, which are used in front of the arithmetic logic unit down here to choose which of these sources we're going to use for the A input to the ALU or the B input to the ALU. This one's going to choose the one on the left, and it's going to choose the output of the register file right here, and that's going to go into A. And this one's going to choose the output of this portal to that same register file. That's going to go into B. The function that's going to go in here is going to be whatever operation we're trying to do, be it add or subtract or what have you. The ALU will do the calculation having to do with that function. The result will come down here and go down to this selector now, which is called the write data selector, WDSEL, which is used to decide which source of data we should use for the register file where we're going to be doing a write. Notice there are 3 ports to the register file. One for reading, another one for reading, and a third one for writing. The 2 read ones are used to source the ALU in this case, and the write one is going to be used as the destination for where the output of the ALU is going to go. And so that data is going to flow down here because we're going to put a 0 into WDSEL to choose this left-hand path, and then that data is going to appear right here. And then the write address, where is that going to come from? Well, that's going to come from RC, which actually is a nickname for this thing up here, because register C is the number of the register that we want to write the data into. And that's going to come down here, and it's going to tell us the address that we want to write the data to right there. And it turns out that there's another bit having to do with the write enable on the register file, which is called WERF, W-E-R-F. And this is not from Star Trek. It's actually W-E, not W-U-R-F, or W-O-R-F, I guess it's in Star Trek. No? Yes? WERF, right? Okay. Okay. So, WERF is write enable register file. And if this bit is a 1, then the register file, when it gets the data and the address here, will write that result into the register file. And the reason that we need this write enable is that some of the time we're going to be doing operations where the register file is not the destination, and we won't want to write the register file. So this is just like that little tab on a disk or something that says whether or not you can write the disk, right? This says whether or not the register file should be told to do a write. And so that's basically how it works. Notice there are two paths. One thing on the left where we increment the PC and put the result back in the PC. The other one where we fetch the instruction that the PC points to, we decode it in this way, and we look up in the register file RA and RB, and then we write the result into RC. So this is it. This is all the hardware that you need to make a beta work.
So the connection between RC up in the kind of middle and the RC down in the lower is
these are exactly the same.
drawn.
It is not drawn. What I could have done is I could have drawn a wire that came down here, but it kind of would have messed things up. And maybe the next time that I do this, I'll draw a wire here. These are the same. If you see two things and the letters are the same, then they are the same. Okay.
And where do the selector values come from?
Well, that's a great question. There needs to be some mechanism for coming up with whether this should be 0, 1, or 2, or whether this should be 0 or 1, or whether this should be 0, 1, or 2. And what's not drawn here is that the opcode goes off to nowhere. And these selectors come from nowhere. And it turns out that there's going to be this whole cloud that we're going to talk about the next time, which is going to be the control logic, which will look at what the opcode is and have a table for every opcode. There will be a unique combination of ways to set each one of these selectors to sort of choose which way the data goes. Anyway, that's an excellent question. A really excellent question. Not just what I said the last time, which was the usual, that's a good question.
Thank you for all of us.
Thank you for everything. Okay. So now that I've given you sort of the first exposure to this thing, let's back up again and talk about exactly how each one of these parts work. Let's talk about a memory port, first of all. Whether this is the register file or the instruction memory does not matter. This is a device which is an access port to a memory. And there can be more than one of them to the same memory. What we do is we put in an address over here. This may be a few bits. In the case of the register file, it's just 5 bits, right? In the case of the big, slow memory, it may be 32 bits, okay? We really don't care. But a number of bits goes in here, and as a result, a short time later, the memory produces a result out Q here. So it goes in A and it comes out Q, and what comes out is the contents of the address given by A. So it's just looking things up. And remember, the address is nothing more than a measure of how far from the beginning of the memory is the data that you're trying to find. And this is, of course, set up as a bunch of 32-bit words. So that seems pretty straightforward. Let's take a look at a data register, something a little bit more complex than that. A data register is sort of the most primitive memory that there is. And in particular, it can only remember one thing, one 32-bit word. And it has two inputs, D and E here. And it has another input called a clock. And then finally, it has an output Q. And let's see if I can explain how this works. Well, it's a good thing that Phil likes to take pictures because we have all these gorgeous pictures on the walls here. But believe it or not, the register right here works exactly like a camera in the old days, okay? In particular, or actually not quite the old days, because I think in the old days there wasn't an on-off switch. But think about a typical SLR camera. It has a switch to turn the camera on and off, and it also has a shutter which you can press in order to actually take the picture. And of course, there's the image that you're trying to take the picture of, and then there's of course the image that gets put on the film. The way that this works is just like that. If the enable, which is the on-off switch to the camera, is off, you can hit the shutter as many times as you want. Nothing will happen. Okay? On the other hand, if you turn the enable, which is the E input to a data register on, then when the clock goes off, and the clock is like the shutter, the data register will take a picture of the data that is at the input and propagate it to the film that is the output. Okay, so every time the clock goes off, it takes a picture of D and makes Q be the same as D. Did you guys do the thing in the scheme course with the press buttons in the data path?
Yes.
Okay. This is very much like that. Okay, this is like the button they talked about in the scheme thing. Okay, it's a little bit different in that this is a little bit more real, whereas the button said, you know, we let the data flow through to the other side. This is very much more close to what the hardware actually does, which is you press the button here, the clock goes off, and whatever is over here on D is frozen in time. So if the person is moving when you take a picture of them, you get a frozen picture and is held on Q until you press the button the next time. Okay? And furthermore, pressing the button doesn't work unless the enable is on, unless you've turned the camera on. Alrighty.
Is this storing the value of D?
It actually is. It is storing the value the same way that the film would store the picture, so that the person can now go and do something different, and the film's got that picture, and it continues to present the picture until you take the next one. Okay?
Oh, so, okay, once it's been stored, Q constantly flows out. You
Q,
don't have to do anything to get
there's
the
nothing
data
else
out.
that you need to do to get the
Constantly
data out.
flows.
Right. Yeah. Q will have that value from the time you take the picture until you take the next one. So here's a timing diagram, and this is sort of the first that you're actually seeing waveforms that look like this. And because we're taking this course in the direction of starting kind of with software and instruction sets and going down to physics, you don't need to worry about whether this is a voltage or a current or a pressure of some fluid or whatever you have, except to understand that there's sort of an idea of things being digital in this course, where this might be a 1, for instance, this high value right here, and this might be a 0, this low value over here. And saying that I press the shutter is sort of like saying that I go from a 0 to a 1. Okay? And this is time going by on the x-axis. And the idea of how the register works here in this timing diagram is that this is the shutter that goes off here. It goes click, right? And here's the data. Now the data, we don't know if the data is going to be a 0 or a 1. And so I express the ambiguity that we're not sure if it's a 0 or if it's a 1. Doesn't make much of a difference, except that we know that when the clock goes off, whatever the data value was, a picture will be taken of that, and the result will, after a short time, and this is the time that has passed by, be put on the output of Q here. So here's the output, the picture that this thing is going to take. And so if this was low before, when this clock went from low to high, then the Q output will be low after a short time, and it will stay low until the next picture is taken. On the other hand, if D was high, when the clock went from low to high, it would be high, and this goes from low to high. Okay? And furthermore, this is what the old picture was. It may have been high, it may have been low, but after we snapped the shutter, the picture sort of dissolved for a little while, and we're not sure what happens during the time when the picture is changing from the old picture to the new one, and then it resolved to be the new picture. And it stays that way from then on until we take the picture again. Furthermore, we needed to ensure that the camera was turned on, that the enable was high during the time that the clock was gone from 0 to 1, when the shutter was pressed. Okay, and so that's the model of how the register works. Now notice over here, if the enable is low, in other words, we didn't turn the camera on, and it had an image in it, a Q, that was either low or high before the clock went from low to high, then it doesn't matter that we made the clock go from low to high. It doesn't matter that we press the shutter, because Q will just still stay with the same value forever and ever, until the next time when the enable is high and we turn the clock from low to high once more. Okay, so it's a mechanism for taking a snapshot of the data on D, propagating it to Q, and the only trick is that whether or not the snapshot actually is taken is predicated on E being high. So that's the enable for the system. Yeah?
Is the data on D just a bit? You're saying it's high or low?
Right, so what I'm showing here is just one bit. In fact, the registers come in many different flavors. This is a single bit one, but the ones that we're going to be using by and large are 32 bits wide. So in fact, there are 32 bits worth of data that are being processed at the same time.
On a single clock tick?
On a single clock tick, and with a single wire controlling whether or not the enable is high or low. Okay, so flash, all 32 bits get stored.
And so this
Yeah.
This thing means the data.
It's not getting destroyed. It's just not getting its picture taken. So, you know, if you're the data and I try to take your picture, right, and the camera's off, no picture gets taken. The old picture that was in the camera is still there.
No, but okay, yeah, I guess I mean when it's enabled already.
Oh, if it's enabled, the old data that is stored disappears, yes. So maybe the right way to think about it is not necessarily in terms of film, because you think of the film kind of moving forward to the next one, but sort of as a freeze frame thing. You guys ever seen, like on a digital camera these days, you can sort of push the button halfway and it'll freeze the picture? I don't know if you've ever seen something like that, but think of a thing where, you know, as you move the camera around, when you push the button, it freezes the picture. And then you can move it around some more and push the button again, and it'll freeze the next picture. That's sort of what it is like. Yeah?
What controls the
Whatever you'd like. So E is an input to this thing that we're going to turn on and off before the clock goes from low to high. And so some of the time E will be high, in which case we say, go ahead and take the picture. And some of the time E will be low. Let me back up just a second here and show you the picture here. The E in this register file is actually called WE for write enable, okay? And when this is high, it says, when this clock goes off, take this data and write it. If this write enable was low, when the clock went off, it would do nothing, even if there was some new data here. So it's a way of sort of disabling the action of a write when the clock goes from low to high. Part of the idea here is that these clocks, you'll notice that the system here has no clock except for down here. A clock is given by the arrow sign that's on the left-hand side here, okay? And so every time we want to process the next instruction, there's going to be a upward going clock on each one of the arrows down here. And the PC will always be incremented, or it will always change. So the clock that goes into here, notice that there is no E here. So this part of the storage here, the register that is the PC, will always be written every clock cycle, every time the clock goes off. On the other hand, we have two other portals here for writing, one being a portal into the register file, the other one being a portal into the big slow memory. And when the clock goes off here, sometimes we're going to write into the big slow memory and sometimes we won't. That's determined by whether or not the WE here is high or low, whether it's a 1 or a 0. In the same way, with the register file here, whether or not we're going to write into the register file will be determined by whether the WE here is high or low when this clock goes off. But the timing idea is that every instruction is transitioned from the present one to the next one by the clocks going off on the bottom line here.
And the three clocks on the bottom line go off at the same time.
Simultaneously. So it's like a drum. It goes bang, bang, bang. And every time those clocks, it's the same clock for all three of them. Every time the clocks go off, whichever writes are turned on happen. And then the new data percolates back through this thing and percolates and percolates and percolates. And if we've left enough time for it to get through, which we're going to talk about how to make sure that we do leave time for it to get through, then it's ready for the clock to go off again. Bang. Time for the next one. And it percolates through again. Bang. Time for the next one. But sometimes we don't want to write the data into these things. So we have a way of disabling the write, even though the clock goes off. Now, you may say, why not just not push the button, right? It turns out that trying to disable the clock is more difficult than saying, go ahead and let the clock take place, but just don't do anything. And we'll talk about why that's true, too.
So the opcode controls that?
So in the end, yes, the opcode will control everything. The opcode will be decoded by some control logic on the side, and will control how each of these selectors is told what to do. It'll control the ALU function telling the ALU what to do, and it will also control the on the memories down here telling them whether or not to pay attention to the clock and to store something new. Shine.
So Gil, the analogy for the camera is more like you have this camera that keeps going off, taking pictures at regular intervals, and then you
Right.
decide when you go on and actually turn the camera on so that one of those pictures actually
Happens.
happens.
Right, so the shutter is being pressed every clock cycle. But the camera is being turned on and off by a little guy on the side.
Right.
And sometimes you push the button and, you know, if the camera's old, the button seems to be locked. And if the camera's new, it just doesn't go beep, I guess.
So your ability to turn the camera on and off is going to be, you're relatively quick compared to the
That's right.
to the clock.
Right.
In other words, what I want to point out is that maybe it's not obvious, maybe it is, but the enable signals get set faster, relatively speaking, than the
Right.
clock is going.
Right.
The clock's ticking millions and millions
It is
seconds.
very important that the logic that controls whether the camera is turned on or off makes that decision before the shutter gets pressed. Okay, because otherwise it's like, whoops, it was too late, you know, and the picture got taken and I didn't mean for it to get taken. So in the same way that we have to make sure that the data percolates through here before the shutter is pressed, we also have to make sure that the decision, which is based on the opcode, to decide whether or not WEMEM and WERF get turned on or off is also made before the clock goes off. And we're going to have a whole class on how the timing of this thing works. But for now, I think it is good enough to just say that we're going to leave plenty of time for this to happen.
Is it
Before
generally
the
one
clock
clock
goes off.
cycle per
Per
movement
opcode.
down there?
Yes. So the data moves through all of this stuff, and then the clock goes off.
Oh, that whole thing is one clock cycle?
Yes.
Oh.
Yeah. There is nothing here that holds up the data. If you remember, the model of the memory is that as soon as an address comes in here, it figures out what's at the location that the address points to and that the data comes out. These things, if they're set one way or the other, the data will flow. The data will flow, and it'll just flow down here. And then it'll finally get to the lens of the camera, which is the data inputs on the memories here, and there it will wait until the shutter is pressed on all three of these things down at the bottom. Yeah.
Well, it looks like we're doing reads and writes on memory and reads and writes on registers
Yes.
at the same time.
Absolutely
At
right.
the same speed.
Yes.
And so
That's an excellent question. So, and that's a really excellent question. We are going to talk about what it means to do a read on a memory here, and is that as fast as a read on the register file. And I just got through a whole lecture saying this is big and slow and this elephant right? But it turns out that there are all kinds of tricks for trying to make this thing faster. But the other thing to note is that even though that this is a operate class of instruction like an add, but notice that this is not being used. So even though it's in the data path here, and notice that this isn't being used either. This is the write to the memory, this is the read from the memory. The only part of the memory read that's being used is this one here, which is where we're fetching what the instruction is that we need to do. And it's going to turn out that there's a thing called cache, okay, which some of you, of course, know, which is going to be used to try to give the effect of speeding up the memory system so that these slower parts do not become a bottleneck to the operation of the whole thing. Because if it weren't for this part and this part and this part, which is the big, slow memory access ports, the whole thing could run much faster. We wouldn't have to wait so long until we clock it the next time. But that's something we're going to be talking about for the future.
Each of those lines represent more than one.
Bit, yes.
So-
Each of the lines here is 32 bits worth of data. Okay?
And are there 30? In reality, there are 32 wires, or
Yes.
Okay.
And that's in general true. For some of these, it's not quite true. So RC is only 5 bits, right? But I don't want to worry about things like that, okay, for now. It really doesn't matter whether it's 32 bits or 64 bits. And if I were to go through here and mark these all, the picture would get full of noise, and you wouldn't be able to see the forest for the twigs, as it were. Okay. Let's talk about the register file, okay? Now, this is beginning to look complex. And the reason it looks complex is because I'm trying to show you all 3 ports at the same time. And the reason in the other diagrams and from now on that I'm not going to show you all 3 ports at the same time is because it gets very crowded when you try to do it this way. So we have RA1 coming in here, and that produces RD1 a short time later whenever RA1 is fed in. RA2 is the second read port to the register file, which produces RD2 a small time later as soon as this thing is fed in. We also have the third port, which is the write port, and that's WA, which is the write address, WD, which is the data that you want to write into that particular place. Here is the enable, turning the camera on and off, and the clock. So these parts here have to do with the write part of the register file, and these parts here have to do with the read part. And so let's take a look at the timing diagram now and see if we can understand how this thing goes. First of all, the clock here is going on and off and on and off, but that has nothing at all to do with what's happening in these first two lines. So I want you to think about all this stuff down here as not making any difference for the next minute or so. RA has some indeterminate value that we don't know, and then finally it settles down to either a high or a low on any of the 32 bits that it has, and the value that it has is A. A is an address. A short time after it goes from having something that we don't know to settling down to having an address A, the register does its work, and after a short time the data comes out of RD, and that is the contents of A. And that's what a read of that register means. Now, it doesn't actually matter when this takes place. If this happens here, then this time afterwards it took place. If it happened here, then this time later it would take place. It's what we call a combinatoric device, which means that the output is only dependent upon the combination of bits of the input. As soon as the address is presented, a short time later the data gets settled down. Now, by contrast, the write is happening in what's called a clocked mode. Okay? And what that means is that it only pays attention to when the clock makes a transition from low to high. This is when the shutter is pressed. And if the write enable is high during that time, if the camera is turned on during the time surrounding the time when the shutter is pressed from low to high, then if you also present an address on WA and some data on WD, then the register file will do the work of making the new contents of the address that you give it A be written into the register file. On the other hand, if you have a low to high transition on the clock and WE is low, then you can have junk on these two things because it won't listen. Okay? It doesn't matter what you put in front of the camera when you try to press the button if the camera is turned off. Right? It could be a scene of anything, and it won't take the picture. Okay. So that was the hardest thing to get through, okay, if you understand how the registers work. Let's take a look at the easier things. These selectors, they're also called multiplexers or muxes, are things that are used for choosing one of n different inputs for a particular output. And the way that they choose it is based upon a select control, S, over here, that comes in. And this may have several bits to it. If it has k bits here, in general there are 2 to the k different combinations of ones and zeros you can put into S here. And so a k-bit input as a selection into one of these selectors will be able to choose one of 2 to the k different inputs to be passed through to the output. It's very much like a, not really a turntable, but a switch in a railroad yard, where we have one output track for the data to go on and several input tracks that a train may come in on. And we want to choose which way the track is set so that the train will be routed to the output, again, depending on how k is set up. Okay? Now, of course, this is shown here with only one bit going into each one of the inputs here, but in fact you can have a wider number of bits, perhaps 32, and that's being shown sort of by the multiplexer being thick here, and when you set a particular selection in here, all 32 bits will be chosen to pass out to here. And in general, this is the kind of selector that we're going to use. Okay. Again, it's a combinatoric device, and what that word again means is that there's no clock involved at all. As soon as the data inputs are there, as soon as the selection is made on S, a short time after those data bits and selection get set up, the output will be produced over here on Q. Okay, so that's a way of choosing which piece of data we want to propagate forward. So, with that in mind, let's again go through this picture, which is exactly the same as the one before, of how an add between two registers resulting in a third register would take place. So we've taken this register, which is the PC, and broken it up into two halves. It's actually the same box, but this is the right part of it, which consists of D and the clock. And here we assume that the E is on all of the time, that the camera is on all the time. And here's the Q, which is the last thing that it had. And we just add 1 to it, and then we have the selector choose the left-hand path by feeding a 0 in over here for PC SEL. And then when this clock goes off, it will snap a copy of the data here on D. And what is the result? If the PC had a particular value in it, n, before, when this clock goes off, what will be written into the PC is n plus 1. Okay? Now, notice that as soon as the clock goes off, n plus 1 begins to race around here and turn into n plus 2, and then pretty soon what's in front of the lens of the camera, which just took a picture of n plus 1, suddenly morphs into n plus 2. And so you may kind of think to yourself, oh my God, did it take a picture of n plus 1, or did the data run around and become n plus 2? Or maybe n plus 3 if it went around a few more times, or n plus 4, or n plus 5. If you remember the push buttons in the scheme book, the push buttons were supposed to only allow one piece of data to go through. And in fact, the way the shutters work on this thing, and we're going to talk in detail about how computers can be built so that this is true, is that the shutter only allows one piece of data to go through. It only takes one picture, and by the time, if this thing just snapped n plus 1, and n plus 1 appears in the picture here, and then becomes n plus 2 and gets in front of the lens as n plus 2, by the time this turns into n plus 2, it's too late. The picture is finished being taken, and you don't need to worry. Okay? It's as if, you know, as soon as you snap the picture, you pull the film out of the camera and you put it in front of the lens. Does the camera now take a picture of what you just pulled out and put in front? And the answer is no, that it's far too late. The lens was open, the lens was closed, and now, you know, things are closed. Okay, the PC comes out here, reads from the instruction memory port over here what instruction you want to do. We choose this left-hand side. It gets decoded into these different fields. And it turns out that for this type of instruction, we only care about RA and RB. And we look up in the register file the contents of RA and the contents of RB. We set the selectors over here to choose the output of the register file and steer them into the ALU ports A and B. We're going to put into the ALU function a function code corresponding to whatever the operation here is that we're trying to do. And then the output of the ALU will be steered down to the right port on the register file right here. We will turn WRF on. Okay, that goes high because, in fact, when the register C code is put into here and the data that is supposed to go into register C gets put there, and finally at the end of the cycle when the clock goes off, click, and all three of these things take their, or try to take their picture at the same time, what will happen is the PC will get the value of PC plus 1, and the register file will get the new value that's supposed to go into register C. And this guy over here, with WEMEM being low, will do nothing, even though the clock goes off. And that's how we do RC equals RA plus RB. Okay? Yeah?
So if in our addition example, the data gets put into the data is ready to write and then gets written at the next clock cycle?
That's absolutely right. At the end of every instruction, there is a clock that goes off. And that clock says, whatever the instruction was meant to do, let's now write the results. And writing the results means that we increment the PC and we write the results into the register file. And then we're ready to do the next opcode.
So you're writing the last operation and doing the next operation.
Well, you're not really doing the next one. So here, let me see if I can draw a timing diagram for a second. This thing. So here's the clock. I always draw an up arrow over here because this is where the action happens. Okay? We basically think of this time like this, being one instruction. because right after we have the clock go high, right after we push the button on all the registers down at the bottom, the data begins to appear on the top, having to do with whatever that write was. And it percolates down. And during all this time, there's a percolation of data down that data path. Okay, starting at the PC, percolating down, percolating down, percolating down, and then it finally gets to somewhere around here. The data is at the write ports. Okay, it has made it all the way down to the bottom, and it's sitting at D and at WD and at WA, WD and WA, and it's just waiting there. And it's waiting and it's waiting and it's waiting, and it's waiting for this clock to go off. And then the clock goes off, and that marks the end of the instruction and sort of the beginning of the next one. And then the next one starts, and again we get the percolation of data down and down and down and down. And then finally that ends with everything waiting at WD, and then another clock, and we begin with the next opcode. So you can think of these edges, and I've drawn the next one starting here just a little bit, but you can actually think of it being on that line, where this marks the separation of one instruction and the next one that happens. Okay.
The box in the lower right-hand corner named register file, what is that register file?
It is the register file with the 32-bit, with the 32 registers in it. And so this is a port on the same register file that we have this one and this one here. So 2 read ports and 1 write port. And the big slow memory has a write port here, a read port here, and a read port here. Also the same, 2 read ports and 1 write port. So even though they're shown here as 3 boxes, 1, 2, 3, it's actually one system.
But which register is the information being stored?
Into register C. The address of the register that we want to write to comes from here, and that in turn comes from here.
That's all.
So it's register C, yes. So think of it as there being a wire from here to here. And if I were to teach this again next year, then I'd put that wire in. So.
And is it the act of the PC register getting written that takes us back up to the top and makes this happen?
Absolutely right, yes. Yeah. Because otherwise the value of their Q wouldn't change.
And the rest of the system would just...
And everything would just sort of be static. What's neat is that you'll get to see this in action with BetaSim, because you'll be able to draw these things out and you'll get to watch the data flow through. Okay, what changed? I'm going to go up, I'm going to go down. What's changing here? Now you may not be able to see this at all. But what is changing is the difference between this path here, register B, and over here. And when I go like this, instead the data comes from here, C. So what do you think is going on here? Everything else is exactly the same, except the B port of the ALU is going to find its data by B cell being chosen to be 1 instead of 0, by getting data from the signed extender, which if you remember just expands things from 16 bits to 32 bits. And that in turn is going to get the data from C, which is those 16 bits in the instruction words which hold the constant. So this is the way that we're going to handle instructions such as RA op C. In other words, add C, register A, constant into register C.
So the B cell somehow has to be connected to the opcode.
Absolutely right. And we're going to talk about the logic that's going to be used to decode opcode and put out a control for B cell, depending on whether the opcode is add or add C.
The signed extender is simply incorporating a minus.
Right. And what it actually does, and we'll talk about this I think in the next class, is it takes the high order bit of the 16 bits and replicates it in 16 more bits to the left-hand side. And that makes a 16-bit signed number the same as a 32-bit signed number. Okay? Good? Okay, let's take a look at branches. First, let's review how they work. Branches are these things that test register A, and depending on whether or not the contents of register A are 0 or not 0, and depending on what kind of branch we have, whether we have a branch that checks for not 0 or a branch that checks for 0, we conditionally update the PC with an increment of where we are right now. In other words, we use the label that's in there as a displacement to the PC. Also, we do this thing where we save the next location to go to after the branch into the contents of register C. And if you remember, that's used for doing a subroutine call where we want to branch back to wherever we came from, or jump back to wherever we came from. So there's actually sort of two steps that happen. One is that RC gets the contents of PC plus 1, and the other is that we test RA, and depending on whether or not it's 0, we either continue our merry way along, or we change the PC according to the displacement given in the constant field of the instruction. The unconditional one we decided was just a BRZ on R31, which is always 0. And then finally, there was this idea of what's called an indirect jump, where we find the contents of RA, and we put the contents of RA into the PC, and we also precede that with the same business of saving where we're branching from into register C. So let's take a look at how we do that. This one here is a branch. Okay, RC gets the contents. This is kind of hard to see, but it says RC gets the contents of PC plus 1, semicolon. If the contents of RA is equal to 0, then PC gets the contents of PC plus the constant C. So how does this work? Well, let's take a look at this business of the PC first. First of all, we're taking the PC over here on the left, and we're going to add 1 to it. And we're going to take that PC plus 1, and we're going to take this path over here that goes into this multiplexer over here. And if you remember, this guy used to be over here on the left, taking the output from the ALU and putting it into the register file. But now, what goes into the register file? The contents of the PC plus 1. We're going to choose this path here, path 1. We're going to make WDSEL be 1. And so contents of PC plus 1 will go into the right path here. Now, which register will get written? The one indicated by register C. And so this is the way that we implement the first part of this instruction, which is remember where I came from. RC gets loaded with the contents of the PC plus 1. And that's happening along this path right over here. PC plus 1 goes into the register file written as RC. Nice?
On these diagrams, when lines cross, they're not...
Oh, yes, I am sorry. Yes. It is in general the case, this has changed since the 1950s and stuff, but in the 1950s, people used to do this. So this was 2 wires that were hooked up, and this were 2 wires that were not hooked up. Okay? So this is the 50s. Okay? But then people got smart and said that this is 2 wires that are not hooked up. Okay? Well, actually, there was an intermediate stage. There was the 1960s. Okay? These were wires that were hooked up, and these were wires that were not hooked up. And the trouble with that is if you Xerox this many times, it starts to look like that. And sometimes when you Xerox this, it starts to look like that, so it's bad. So the new way of doing it, since the 1970s, is that these are wires that are hooked up, and these are wires that are not hooked up. So I'll put this as connected, and these are not connected. And of all these methods, this is the only one you should ever use. Okay? So any things that meet at a point, they are not hooked up. And if you want 4 wires, then you have to do this. And 3 wires, it's clear that they must be hooked up, because why else would you do that, right? So just a bit of draftsmanship here. And it turned out that they didn't do this because in the beginning, writing a piece of CAD software, people didn't know how to draw arcs. So we could draw them by hand, but getting a pen to draw them on a piece of software was hard to do. But they sort of look gross anyway. So. Okay, so wires across are not hooked up. So now we've handled storing the PC plus 1 into register C. Now we've got to test the contents of register A and see whether it's 0 or not. And the way that we do this, and unfortunately I kind of didn't quite do it all the way here. The instruction comes in here just like it always did, and comes out here and is decoded into different fields. Okay? The register that we choose to be register A comes out here and gets read here, and unfortunately I didn't make this read by last night, but the output of the contents of register A comes out here and goes out here and goes into this gate here, which we're going to talk about in the next class, which is a gate to test whether or not the data there is 0. And that comes out as Z here. Is it 0? And so we're going to test the contents of register A like so. And whether or not it's 0 will then control, through the same control logic that looks at the opcode, is going to control whether or not PCSEL gets set to 0 or to 1. If PCSEL is set to 0, then the PC will be loaded with what? With PC plus 1. And we'll just go forward to the next instruction. We will not take the branch. If, on the other hand, PCSEL is set this way, and that's why both of these are red here, if we choose this path, then the PC will be loaded with whatever pops out of the ALU. And what's going to pop out of the ALU is going to be PC plus 1 plus, and we're going to set this to plus, what comes out of this path, which is the sign extended constant C. So the ALU will be told to do an add, and the result of the add of PC plus 1 plus C will be spit out here, and that will go into the PC instead of PC plus 1. And the control over that will be whether or not this little Z here is high or low. In other words, whether the data that's coming out of register A over here is all zeros or whether it's not. And that's how we're going to do a conditional branch.
So both those occur at the same time?
Yeah, so, okay, so you're actually, that's also a very good question, really, which is that I have effectively done this little sleight of hand, and before we said first the PC plus 1 gets put in here, and then we do this. And the answer is that this circuit that I've shown you with all these clocks going off at the same time does them both in parallel at the same time. And the answer is yes, you're absolutely right. But we're going to be careful so that you won't be able to know the difference. And the way that you're not going to be able to know the difference is that the sum that this guy does of the constant with something to do with the PC, I could have had this path choose the PC before the plus 1, and it would have chosen the PC before PC plus 1 was put into PC. But instead, I choose the data having to do with PC plus 1, in other words, what's about to be written into here. So the effect is as if we did them one after the other. Okay? So the functional description is one of these happening in sequence, but the physical implementation is that they happen at the same time. Okay. A jump. A jump is very similar to a branch. Let me go back and forth here. What is going to change? Isn't this cool? Okay. I'm sorry you can't see it, but anyway, this red shifts from here to here. Well, you can at least see these things moving, right?
Yes, I can.
Okay. And so instead of saying that we're going to take the PC plus 1 and add C to it, what are we going to do? We're going to take the contents of RA and add C to it. And that's what jumps do, right? Contents of RA plus C goes into the PC. And one other change takes place. Instead of there being a conditional, which is down there, you'll see that it may take the left-hand path, which is to not update the PC, or it may, or it may take the right-hand path, which is to update the PC. We're always going to update the PC with the addition of contents of RA plus C going out to the PC, because jumps always happen. Okay. Isn't this fun? Okay, we're just about there. Loads and stores. This is a way of moving things from the memory system into the register file and vice versa. Remember, load takes the contents of RA plus C, uses that as a pointer into the memory file, and puts the result into RC. Stores actually work in one of two ways, and I noticed, unfortunately, yesterday, you guys printed out a reference thing for the beta, not from the last term that I taught it, but from the term before. And we actually changed some stuff. And so one of the other things I'm going to do when this class is done is I'm going to ensure that we get the right stuff out to you guys. Because we used to do this so that stores worked like this, where the contents of register C was written into the memory location given by the contents of register A plus the constant C. And we actually turned it around. Now, in the assembly language, it didn't matter. Both of these always flowed from left to right, like I've promised all things do. But in the encoding of the bits, this changed from, in the old setup, the encoding of the bits was actually from right to left. And I decided it was important to be consistent. In the last term that I taught it at MIT, I made it be from left to right in the bits also. So first of all, be aware that you may get confused, but that the new way, okay, is everything is left to right. And if it doesn't look left to right, then you're looking at the wrong thing. And you should, raise your hand and talk to your TAs and find out where the latest version of the documents are so that you can see it going from left to right. Let me show you. I'm going to actually skip this because it'll take me longer to tell you about the difference between left to right and right to left, and it's always left to right. Okay. Here's a load. The PC gets one added to it and gets overwritten with, so that the next PC is going to be the next opcode after a load. It's not a branch, right? So anything that's not a branch will always choose this path, and the updating of the PC is a straightforward thing. The actual execution of the load, however, is kind of neat. What do we need to do? We need to find the contents of RA, and we need to add C to it. In that way, it's very much like one of those standard arithmetic operations that's taking the contents of RA and adding C to it. And so the instruction comes in here, it gets put out, we take RA and C, take them, steer them to the ALU, do the add, and what pops out of here is the contents of RA plus C. But instead of now taking this data value and writing it to a register, like add C, RA, comma, some number into RC, we now feed it into a read portal on the big slow memory. It goes into RA2 here, and a short time afterwards, RD2 tells us what is in the location pointed to contents of RA plus C. So it's doing mem of contents of RA plus C and looking it up in the big memory. That comes out here, and the value of what's inside of here, not that thing itself. You see, this would just write the contents of RA plus C if we chose this path. But if we choose this path, it says what is in the memory location pointed to by the contents of RA plus C. And that gets fed to the register file here. RC says where we want to write it to in the register file. This says we really want to do it. Clock goes off, bang, the load happens. Okay? So this is where we're doing the fetch here from the slow memory, the big slow memory.
Can you interchange things in slow memory without going to the register?
No. No. And that's kind of a shame, except it turns out that most software doesn't want to do that. So towards the end of this class, we're going to talk about all kinds of trade-offs that we've made here, like why it is that we chose this structure as opposed to others. And so the structure here, and this is very typical of RISC systems, is allow a lot of things to happen in the fast memory and have a very sort of clumsy, slow load and store to move things back and forth. But we'll talk about why that is. Okay, load to store. Let's go back and forth. Here's a store. In a store, we're not going to be using the read stuff at all, and we're not going to write to the register file at all, so you'll notice this is all dark. Okay. However, what we are going to do is we will use the write path of the slow memory, the big slow memory, and that's over here. And this is now being turned on for the first time. So WEMEM is now on, and the data that pops out of the ALU is going to go to the memory system. Now, what data are we actually going to put in there? The contents of register A. That comes right over here and goes straight down into here. No computation at all is being done on the contents of register A. However, the address in the big slow memory that we're going to write the contents of register A is going to come from the ALU. And what location are we going to write? We're going to write the constant C plus the register is the contents of RC. So RC is going to get chosen here. It's going to get looked up, going to get fed into here, and will be added to C, just like it says right up here. And that sum will be used as a pointer into the big slow memory over here, and that will be the location that we write the data, which is the contents of RA that comes out here. Nothing has changed over here with bumping the PC by 1 to get to the next opcode. Nothing has changed up here in terms of fetching the contents of the PC to find out what instruction it is that we want to do. But this is neat because now you've, I think, seen all of the different paths being used in order to do the different types of opcodes that we have. Now there's one that I'm not going to talk about during the lecture today because the last few classes have taken too long, I think, and that's going to be what are called exceptions. In certain cases, we're going to actually want to take this multiplexer right here, this thing, and we're going to want to shift it over to the right. And what that's going to do is it's going to not do an instruction that we want to do. Instead, it will substitute in an instruction saying branch if 0, R31, XADDR, comma, XP. Remember, XP was that exception pointer register I pointed out in the last class. And what that instruction is going to do is going to say stop what you're doing and jump to the location XADDR. Do a branch to there. And remember where you came from in XP. And that's called an interrupt or an exception, and it basically is a way of sort of stopping the processor along its path and suddenly doing something else because some perhaps disastrous thing has taken place. One example is, for instance, if the code is running along and it divides by 0. In general, that's a bad thing and you want to stop, right? If the code is running along and somebody presses a key, you would like to listen to the key. So instead of having the program go around and check, has he pressed a key, 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 that's a sort of a inefficient way to do things. What we do instead is we have an idea of an interrupt, which means that when a key is pressed, whatever code is running at the time is stopped. We jump to a handler to handle the person pressing the key. When we're done handling the key, we jump back to where we left off. And so it's a forced subroutine call that we didn't expect. We didn't know when it was going to take place. And so I'm not going to talk about the detail of how that works, but know that the mechanism here is for handling those types of things. Okay. There's one more instruction. This was actually kind of a neat one. What happened is that after the beta was designed and we were playing around with it for a few terms at MIT, I think Steve Ward discovered that we could do an instruction that we didn't think we could do before, and it's called load relative. And the idea is if there's a big 32-bit constant that I want to load into a register, an easy way to do it is to use this instruction called LDR. And all that I have to do is, let's say I want to load the number 1, 2, 3, 4, 5, 6, 7, 8, 9 into R1. What I'll say is, well, let's put the number right here, give it a name, and say load relative this label into R1. And if you remember, what the assembler will do is it will figure out the distance between this opcode and the label right there, and it will put that distance into the constant field here. Okay? And what we want it to do is take this number, pluck it out of the instruction stream, and put that number into R1. And then, since the number is kind of in the way of the code here, right after we do this, we branch to a little bit after that, to this place +1, and that'll take us to down here. Okay, so it's a very handy way of bringing big constants into our system. Well, it turns out that LDR can be implemented in the following way. LDR. Well, we want to take the contents of the PC +1, add a constant to it, look that up in the memory, and put that into RC. Well, here's PC +1. We take that over here, feed it into the ALU. Here's the constant. We feed that into the ALU. PC +1 plus C comes out here. We feed that into a read port on the big slow memory. And the data that comes out of that is chosen here. And then we put that in the right port of the register file, feed RC into here, turn this on, and go bang, and it does this opcode, LDR. And so it's just a way of saying, find a word close to the PC right here at a certain distance from the PC and load it into the register file. So, sort of a fortuitous extra thing. Okay, let me give a little bit hint into what we're going to do in the future now. And this has been talked about by several people that have asked questions as well. There is going to be a table. And the table is going to be one that looks like this. It's going to say, depending on what the opcode is, and here's the different opcodes that we have. Op is just a sort of a grab bag for things like plus and minus and things like that. Op-C is for the same things with the C at the end of them. Load, store, branch if 0, branch if not 0. This is kind of an old style here. Jump, LDR, and those things that we shouldn't let take place. And given those opcodes, given whether or not that thing that was testing whether the contents of register A is 0 or not 0, and given whether or not there is an interrupt that we're trying to do, and again, we're not going to talk about this quite yet, depending on all of those things, we will want to control these outputs being the selectors, PC-SEL, RA2-SEL, A-cell, B-cell, and WD-cell. All of these things will be controlled in a different way depending on what kind of opcode we're trying to do. And then finally, the ALU function will also be controlled depending on what we're trying to do. And then the write enables that go to the 3 files down at the bottom will also depend on what we're trying to do. In all of those cases, you can fill in a table here that fundamentally is taking, in this picture, an indication of what is the opcode, what is Z, and depending on those things, what should each one of the other control inputs to the selectors and to the E inputs down here, whether they should be on or off, what path they should choose. And actually, even after this class here is done, you should be able to fill in a table like this to figure out just exactly how it should be set up. And we're going to talk about that and how to implement a table which will then show you completely how the system works. The other thing we're going to do the next time is we're going to talk about a circuit that looks like this. And again, you open the hood of a car and you look at this and you say, oh my God, right? It turns out that this is a 4-bit ALU, okay? And these things over here are AND gates that do AND. These here are NOR gates, which do OR and then take the inverse of the output. And these are NOTs up here. And we're going to talk about how you can look at a picture like this, and by the end of the class, you will understand exactly how this thing works. Okay? And you'll be able to tell your friends just how it works. And this is a 4-bit one, but it works the same way no matter how many bits you are trying to do. So that's going to be the lecture next time.
That has the old style connected dot.
This has the old style dots in it, yeah. Well, this has a redundant set of dots. I don't believe, so it's not, this isn't quite true. So halfway in between here and here, there was a style, so that's 1970s, I think. There was a style where this was not connected and this was connected. Okay, and that's very, very close to that. Okay, except I'm drawing it the wrong way, right? This one on the left is connected. This is connected, and this is not connected. So I think what they did there is that they put in the dots, even though if you took all the dots off, you could still see how the circuit worked. I don't think there are any junctions of 4 that have dots on them, at least as far as I can tell. Yeah. So, yeah, it's been a nice long road, but I think that last answer is really the right one. Okay, are there any questions? Good. Okay. Great. Have a great lunch, and see you tomorrow.